Hi, my name is Luca. 7 years ago, I tried to build my first electric surfboard. I used an inflatable paddleboard, some RC car batteries, and a waterproof drone motor. It technically worked, but it was very inefficient, very slow, and you could even swim faster. A couple of years later, I moved to a real board. I took an old windsurf board, shortened it, cut it open, and started building a brand new propulsion system. Inside, everything is still very simple. A fiberglass reinforced wooden box for the main propulsion enclosure, a 70mm water jet system from AliExpress, a 500 kV motor, a cheap high current ESC, 4 6S LiPo batteries wired in 12S, and a standard RC car remote.
Je crois qu'il y a un peu de l'eau là-dedans, non?
Ouais, il n'y a pas trop d'eau, je crois.
Ouais.
Bordel. Il y a tellement d'eau.
Well, honestly, it wasn't that bad. I mean, it didn't sink or caught fire, but after a few tests, it was clear that the board wasn't really good enough. I mean, it worked, but the efficiency was close to zero, and also the physical finishes were not that good. So instead of trying to patch it again, I switched and started building my own board from scratch. Here's the build. The base of the board is made from XPS insulation sheets glued together into a big rectangular block. I shaped it by hand, cutting the rough lines with a saw. Then I sanded it, first with an orbital sander, then by hand for the curves. It was very tricky to keep the symmetry. Next, I move on to the fiberglass. I mix a 2-part epoxy, 2/3 resin to 1/3 hardener. Then I laid the fiberglass cloth. I applied 3 layers on the bottom and 2 layers on top. About 10 square meters in total. This was my first time working on such a big project. Therefore, I didn't use any vacuum bag system for the epoxy to cure, because it was way too complicated for me. So the finish isn't really perfect. Something I will fix in part 2. Once it dried, I installed the threaded rivets at the rear into the aluminum bars. This is where the propulsion system will be fixed. Then, I started the painting. I used an airbrush to coat the board in a light grey. Well, that's the result after the 3rd layer of paint, and honestly, I think it doesn't look too bad. After that, I glued the anti-slip pad on top, finishing the surface and making it look clean. The cover wasn't great yet. It was just a wooden board with a gasket that wasn't waterproof. Water could sneak in easily. In fact, it was sneaking in very easily. In the future, I will replace it with a carbon fiber plate and a proper gasket. For now, it served as a simple temporary cover. In this new prototype, I was running on a 70mm water jet system, a 500 kV motor, which I know it's stupidly high, a 400 amps ESC, and 4 cheap LiPo batteries. Well, it's even worse. Some of them must have broken down. I think it's the ESC, but could be the batteries as well, as the LiPos are pretty old. For now, I'm planning to buy a new ESC as well and completely redesigning the propulsion system. What you're seeing here is just a simplified demonstration of how a jet impeller can be designed in 3D. The actual turbine used in the board doesn't even have the same shape visually. The real development process was completely different and took a lot more time, roughly half a year to reach a design that gave consistent and convincing results. In reality, I went through dozens of iterations, printing prototypes, testing them in water, adjusting blade geometry and clearances step by step. On top of the physical testing, also use CFD simulations to validate the flow behavior, pressure distribution and overall efficiency before finalizing the design. Okay, the propulsion system is completely finished. There's also now a carbon fiber cover, which should be way more waterproof than the old wooden cover. I just got my brand new battery as well, so we'll go to the lake now, see how it performs. I give a 50% chance of blowing up, 25% chance of going freaking fast, light speed, and the other 25% chance of the battery catching fire or other crazy stuff. We'll see. Well, this was the worst fail ever.
The battery catching fire.
To make a long story short, I ran into a lot of problems with the battery. Water got into the battery enclosure, causing a massive short circuit. The BMS was destroyed, the copper and nickel connections were ruined, and 20 cells were dead. This was a custom-made battery. I had to order it because I didn't think I could build one myself. And after it broke, I didn't even know if I could repair it. I took a few weeks to figure out a solution. I researched everything I could, watched countless YouTube videos on battery construction, learned more about how to spot weld properly, and about a spot welding machine. I also redesigned and remodeled parts in 3D, planning each step carefully to make sure it would work. I had to replace the dead cells, resolder everything and respot weld the battery. To make it more reliable, I replaced the copper bus bar with braided copper wire, easier to solder with my machine and stronger enough for the current. Even then, I made another mistake. I forgot the small insulating stickers on the top of the cells. During spot welding, I caused another short. The battery almost caught fire. I had to replace the cells again, this time adding the insulating stickers properly. After that, the battery was finally solid and ready for the next step, spot welding. and then basic soldering to connect the braided copper to the nickel strip. Well, 3000 years later, the battery is finally finished. I mean, at least the wiring and the soldering, but I plugged the BMS. I have the Bluetooth module on, which is connected to my phone. I have the basic SOC, the real-time voltage, current. And these two are great if I want to calculate the basic efficiency, if I want. And then I have temperature of the main negative and the main positive, and the voltage of each parallel, which is great for charging and discharging balance. The 4 black PG ports to do the main frame, and then a white plexiglass sheet on the bottom, nice plexiglass sheet, screwed, and there is silicone which should be a waterproof sealing, by the way. Then there is those type of connectors, main negative right there and the main positive. That's the main charging plug, which is related to the BMS obviously, and then there is the charging cable that just plug it in like this, bam, charging. There's also this little white thing, which is just a spacer, could have been black, but I had white loaded in the 3D printer. The main negative going here, and I forgot to add the little space for the screws right there. So I had to print another white spacer for the battery to fit inside the battery box. Okay, the battery is now completely finished, finally. But it was pretty tough, as you saw. I almost set the workshop on fire more than one time. But now it's finished, looks pretty good, I think. Also made some slight modifications on the propulsion system, so we'll be going to the lake back again now to get a hopefully more successful test.
Yo! Mec, il y a un truc bizarre, je sais pas ce que c'est, genre. Genre ça vibre giga beaucoup. Et j'ai pas été à fond. Genre, est-ce que ça allait vite ou pas?
Ouais, ça va déjà bien.
Oh non, la GoPro elle est...
T'inquiète.
Elle a pas kiffé là. Je sais pas, pareil, il y avait un truc bizarre, genre ça vibrait beaucoup, genre. L'autre jour c'était mieux, je sais pas, là il y a un truc bizarre là. Ah mais ça veut dire que je dois casser le scotch. Bon ouais non, je pense qu'il n'y a pas d'eau qui est rentrée. Ouais, c'est vraiment un truc bizarre. Je sais pas ce que c'est. Bon, peut-être... Ah, il y a trop de balles, je suis pas à fond. Mec, l'eau, c'est pas là. J'arrive.
Ah, j'ai...
Tu cries comme si t'es un...
Yo! Ah, la GoPro elle est lourde. Attends, je vais mettre...
Ah, c'est pas une bonne idée. Ah, shit! J'arrive! Aïe! Ah! J'ai utilisé combien de pourcents? J'ai utilisé 10%.
I think we can call that a success. I mean, the carbon fiber cover was now 100% waterproof. The new battery enclosure was 200% waterproof, so very good. Unfortunately, I forgot to turn on the GoPro, so no footage of on the board, pretty bad. But also I didn't have any battery blowing up or ESC blowing up. I had some slightly vibrations due to a rusted bearing inside the nozzle, but very easy to fix and not that important. Last but not least, I never went full throttle on the lake, which means the actual top speed should be pretty insane. That's the nozzle I used in the previous test. It worked surprisingly well, but I had a couple of issues with the bearing inside, which hold the shaft in the impeller. Basically, just rusted very quickly, very easy to fix, just change the bearing. Yeah, anyway. Second thing, I had some troubles with this ESC as, I mean, it's dead. I thought it was waterproof, turns out it isn't. So I opened it just to see. There's a couple of MOSFET right there, which are, I don't know if you can see, but they are burns, so it's dead. And also this condensator, which, yeah, there's some rusty sand or crazy stuff, I don't know what it is. Yeah, so it's dead. Don't buy this shit. I have another issue between the ESC and the motor. Since this one is water damage, I don't really want to buy the same. So I need to find another one, but it's very hard because this motor requires a very high ERPM.
ERPM? Let me explain. ERPM stands for electrical revolutions per minute. It represents the electrical switching frequency the ESC must generate to communicate the motor phases, not the mechanical rotational speed of the rotor, which this one is the basic RPM. This motor is a high pole count outrunner with 20 magnetic poles or 10 pole pairs. I initially choose an outrunner to increase torque since the magnetic forces act at a larger radius, increasing the effective lever arm between the rotor and the shaft. However, this torque advantage mainly exists at the lower rotational speeds. As RPM increases, the motor quickly transitions into a power-limited regime. Therefore, it's important to note that this doesn't mean in-runners are inferior. In fact, in-runner motors can perform extremely well, especially at higher rotational speeds, and are widely used in high-power water-jet applications too. Independently from ESC limitations, the motor itself follows a very specific efficiency behavior. This can be visualized using a motor efficiency map, where torque, input power, mechanical power, efficiency and rotational speed are all interconnected. Efficiency peaks only within a narrow operating window. Outside of this zone, losses increase rapidly as RPM rises. The thermal efficiency map tells us the same story. As rotational speed increases, electrical and mechanical losses are converted into heat, pushing the motor toward its thermal limits.
Alright, so that's why the JetBot project stands for now. It worked pretty good. I mean, the board runs, the jets work properly, but I'm not very satisfied with it. I mean, I want to refine the whole propulsion system. Well, I still need to solve the ESC issues while finding another ESC, because I think I spent more than $1,000 on broken ESC for now. I have one there, another one here, 3 here, well, crazy. So I need to find a proper one so that the propulsion system can run properly. I also want to remake the board, because as I said previously, I didn't use any vacuum bag system for the epoxy to cure, so the finish isn't really perfect. So my idea is to sand completely the board again, put some fairing compound everywhere, and then paint it again, so it will be a more professional board. Also, I'm now working on a more 3D printable kit of the whole propulsion system, so that everybody that has a decent 3D printer at home can 3D print it and like build their own jet board. That's the idea. I'm still working on it pretty hard, but that's the whole idea. Okay guys, thank you for watching. See you soon.